that you have in this group. And so, so Mark Fein mentioned, well, talked about definable sets in his talk. I will actually give a definition. So, I mean, even if you have a rough idea of what they are. So, okay, so definable sets are defined by a first-order formula. So, a first-order formula so I will say in the language of groups, because of course it's much more general than this, but we will only stay in that language. So it is a formula of the form so what can be a first-order formula? The first easiest thing is just to have an equation. Okay, so for example, so an equation in a group will be a word in some variables, x1 up to xn, and you declare that this word should be equal to 1. Okay, and then you can look at all the sets of tuples xn, x1 up to xn, which satisfy this equation. So that's the simplest example of first-order formula, but we want to generalize this, so we want also to allow inequations. Okay, and then we also allow to take conjunctions and disjunctions of such things. So it just means that we want, this is a symbol for and this is a symbol for or. So let's say if you have two indices, I and j, 1 to p and j, 1 to q. Okay, so you have a collection of systems of equations and inequations. And then the last thing that you can do is to generalize this by adding some quantifiers at the beginning. So you will have here a sequence of quantifiers, for example, exist x1 such that for all x2 and, okay, just a finite alternation of quantifiers on the variables that you see here. Okay, so that's the most general form of first-order formula in the language of groups. And then a definable set is just a set of elements which satisfy such a formula. So let me just give some examples of very simple formulas. So you can have a formula which says for all y, xy equals yx. Okay, so of course it's not in the completely general form here, but you can easily put it in this form. Okay, and here you see that the variable x is free, so I'm going to denote it in brackets after the name of the formula. Okay, and another example, say psi of x, which says that there exists y such that x equals y squared. Okay, so if you look at the set of elements which satisfy this formula in a group, okay, this will give you the center of the group. And if you look at the set of elements which satisfy this formula, this will be the set of squares. Okay, so the definable sets of a group are all the sets that you can define using formulas. So let's say x in some Cartesian power of the group is definable if there is a formula with n free variables such that x is exactly the set of G1 Gn such that, so this is a symbol which says that the formula phi of G1 Gn is satisfied in G. Okay, so G satisfies this formula. Yeah, let me see. Okay, I should mention here that I wrote here very general first-order formula, but sometimes you want to you want to fix yourself some group, some base group, and you want to add here some parameters that come from the base group. Okay. So for example, here, instead of asking for elements that commute with everyone, you could ask for elements that commute with a specific element in your base group.
You can't really see the green chalk.
Oh, okay. It's blue, so you really can't see it. Red should be better. Okay, so that's G, and you take some parameters. Okay, so that's slightly more general, and then instead of saying that G is definable, you say that G is definable, X is definable over some set A of parameters, say. Okay, so for example, the center of a group is definable, and the set of squares is definable. Yeah, an important remark is that, okay, if X is defined by a formula phi, let's say X with and some parameters A, okay, and if I apply now an automorphism of my group, I take an automorphism of my group, then it's easy to see that the image of X by this automorphism will just be defined by phi of X, theta of A. Okay, that's kind of trivial, but it's important. And in particular, if your automorphism fixes A, then your set is invariant. So okay. Let's say. Okay, so as I said, we should consider a group as endowed with the collection of all its definable sets. And so it means that when you look at subgroups, okay, there is a notion of inclusion which is a bit more restrictive than the usual notion of subgroups. Okay, so what are the natural embeddings in this setting? Okay, think about, you want to embed a topological space into another. You want that there will be some compatibility between the open sets. So here we want some compatibility between the definable structures. And so you say that a subgroup H of a group G is elementary, or that the embedding is elementary. So let me see how to phrase it best. Yeah. Yeah, okay, I should say that a natural way to denote this, okay, if I look at tuples in Gn, is just to say that I take phi of G, okay? This is just all the elements, the tuples of G, which satisfy the formula phi. Okay, so if for any formula, okay, phi, if I want to look at what are the elements of H which satisfy phi, there should be exactly the elements of H which satisfy phi in G and which are in H. Okay, so okay, so this may seem a bit silly, but if you think about this example, if you have a group and a subgroup, it's absolutely not clear that something which is a square in the group and which lies in the subgroup will also be a square in the subgroup. Okay, so this is not obvious, but if you have a subgroup which satisfies this, then you call it elementary. So another way of thinking about this is to say that the elements of H, they have the same first order properties in H and in G. Okay, so for example, if they commute with all the elements of H, then they will also commute with all the elements of G and these kind of things. Okay, so this is the natural notion of embedding, and yeah. Okay, and so here I should quote the first theorem of Thiel, which solved the long-standing Tarski problem, and which showed the Tarski problem was to know whether free groups of different rank are elementary equivalent. But so in fact, Thiel proved something stronger, which is that the canonical embedding of, say, the free group of rank 2 in the free group of rank 3 is elementary. So of course you need okay. So yeah, so that's the definable structure on a group. And then a very important part of the model theory is called, well, nowadays is called stability theory. And essentially the idea of stability theory is that you want to know, so you think of this definable structure on a group as giving a kind of geometry on the group, and you want to understand how good the geometry is. So let me talk a bit about this. So yeah, so I should have mentioned that a big part of the talk will be a kind of introduction to all these notions, but I guess it can't be avoided, and I think it's an interesting way to think about groups. So yeah. So the question is how well behaved is this definable geometry that we have on our groups. So stability theory was developed by Scheller, essentially, in the 70s. Okay, and it really tries to find some conditions by which, so it's not only on groups, it's on more general structures, but it tries to give some conditions by which will guarantee that the geometry will be good in some sense that we will see. So the first notion that Scheller defined is that of a stable structure. So I will give the definition for groups. So a group G is stable. Okay, if essentially there is no formula which encodes an infinite linear order. So what do I mean by this? So I take a formula phi x, y. So these are free variables, both of them, and there may be some parameters, but I don't mention them. Okay, so these are two tuples of free variables. Okay, and okay, so if there is no formula like this, such that for any n, there are tuples, let's say a1 up to an and b1 up to bn in G, such that G satisfies phi of ai bj if and only if I is less than or equal to j. Okay, so it's kind of a strange definition. It's not very illuminating, especially since I told you that this is supposed to guarantee some good geometry. This is really not quite obvious.
Question?
Yeah.
What definition of elementary?
Yeah.
In that equality there.
Yes.
Do either of the inclusions always hold, or can both of them?
No, both of them can fail. I think these two examples give you, no? If you look at these two examples, I think you should, yeah. Okay, so let me see. Okay, so let me state now another theorem of Zlin. So you can give some examples of unstable groups, and okay, of course it's easier to show that a group is not stable because you only have to find a formula like this. To show that something is stable, you have to really understand what all the possible formulas look like and what all the definable structure looks like. So, yeah. So Zlin proved using the tools that he developed to solve Tarski problem, he showed that free groups are stable, so non-abelian. In fact, he showed that torsion-free hyperbolic groups are stable. But let me just state it for free groups. Okay, so according to Schellach, they are supposed to have a good geometry, but let us now see really what this means to have a good geometry. So in fact, what we will see is that to be stable is equivalent to having a good notion of independence. And here, so independence between elements. So here, what you should have in mind is linear independence on vector spaces or algebraic independence in algebraically closed field. So.
One call this property.
So okay, so that's not the original definition. The original definition is in terms of types of elements over sets of parameters. So if you take an element, you can look at the set of all formulas that it satisfies. Okay, that's called a type. And the original definition tells you that for some cardinality, if you take a set of parameters of cardinality kappa, then the number of types is not bigger than kappa. Okay, so it's a kind of, you don't have too many different kinds of elements. Yeah, so there are many equivalent definitions of stability, but yeah. Okay, so let me now talk about this notion of independence. It's called forking independence. Okay, so let me first start with a remark that you have a group, you have a definable set. Okay, so if you fix yourself a set of parameters, you have a certain collection of definable set. But if you add parameters, if you allow yourself to use more parameters, then you refine your structure. You get more and more definable sets. Okay, so here's a trivial example of how you refine your definable structure. So suppose you allow yourself a set of parameters. Okay, so I can build all sorts of definable sets, and then suddenly you give me another element, and you tell me, okay, now you're allowed to also use this element as a parameter. So for any definable set that I had before, if D was definable over A, okay, say think of D as contained in G, it doesn't really matter. So I can say, well, I'll just take D and I remove C if it's in it. Okay, so I have reduced my set D if C was in it. I have a smaller set, but that's not really very interesting. I mean, it's not really much smaller, and I haven't changed my definable structure in any essential way. Okay, so okay, but not much smaller. That's the idea. So the next definition I want to give is, why do I want it to mean that a definable set is much smaller? Right? Okay, so definition. So I will give it in terms of formula, but you should translate it in terms of definable set. So let's say you have a formula with parameters in, so let me say A union C. So I mean A and then some tuple C. I add finitely many elements. Okay, it doesn't matter. You can define it if you add infinitely many elements, but and you will say that it forks over A. Okay, so let's think about it like this. I have this is G. If there exists, so okay, the first point, let's just ignore it for the moment. But so I'm just taking an elementary extension of G. So it means I might take a bigger structure, but I make sure that G is elementary in it. So it's called an elementary extension. Okay, so G elementary in G hat. Okay, and the second thing that I need is an infinite is a sequence of automorphisms of G hat. So I take sigma n in the automorphisms of G hat. Okay, and I require that this automorphism fix A. And what I get is that the sigma n, if I look at the translates of my definable set, but this time, okay, I look at it in G hat. So I ask that there are disjoints, so not exactly pairwise disjoint, but k-wise disjoint. Okay, you can safely think of k equal 2 for the rest of the talk. Okay, so let us try to understand exactly what this means. So I have my set here, and I have all these translates, and they're disjoint in some sense. So sigma n of 5G hat. Okay, so think about a set. So remember that I wanted to define sets which are much smaller than the sets I could define over A. So suppose that I have a set which is definable over A, which contains my original set. Well, set definable over A is invariant under all these automorphisms. Okay, so it means that the picture will look like this. Okay, so it means that inside any set definable over A, which contains my original set, I can fit infinitely many translates of this set. Okay, so yeah?
K-wise means every K tuple.
Yeah, every K tuple are disjoint.
Some K.
Yeah, for some K, yeah. So yeah, there exists a K here also. Yeah. Okay, so this means that really when using my my parameters A and C, I could define a set which is much smaller than any set definable over A. Okay, in some sense. So that's the idea of forking. So and now we can use this notion to define notion of independence. So what is the idea? So the idea is we want to say that that two tuples B and C are independent over A. So let me say it this way. That B is independent of C over A. Okay, so heuristically, the idea is that if I look at if I allow myself A and C as parameters, then I don't get much more information about B. Okay, so it means that if I look at definable sets which are definable over A and C that contain B, they will not be much smaller in that sense than the sets definable over A only that contain B. Okay, so definition. So I will define, okay, so the idea is that if having C as parameters does not give a lot of extra information on B. Okay, so definition. Take A and G parameters and B, C tuples in G. Okay, so I say B is not independent from C over A if there exists a formula. So with parameters, let me stress the parameters, with parameters in A and C, so it's our set here, which contains B, okay, so such that B satisfies this formula. Okay, and which forks over A. So okay, so this is our definition of independence, and the fact. Okay, or with theorem maybe, I don't know. Which I will not prove, but that if you're if the group is stable, then this relation has lots of nice properties. So first of all, you may notice that one bad thing about this definition is that it doesn't look symmetric. Okay, but if G is stable, then the relation is symmetric. Okay, and then you have lots of other nice properties. For example, so it will be invariant under automorphisms, and it has some kind of transitivity property. And so let me state it that way. So if G is stable, so the independence relation has many good properties. Okay, and so also, for example, you can always find someone who is independent from someone else, and as long as you go to an elementary extension and things like this. Okay. So I will just say symmetry. Okay, and in fact, maybe something which is even more interesting is that, if you can show that there is some relation, okay, between tuples. So if you can show that for every set of parameters that you can choose in your group, there is a relation which satisfy all these good properties, then the theory is stable. Okay, so in that sense, being stable means that you have a good geometry because you can define a good independence property. So in fact, if there exists satisfying all these good properties, okay, then G is stable. Okay, so in that sense, it's in that sense that being stable means that you have a good geometry. Okay, so that's one notion. But if we look at our definition set, of what it means for a definable set to be much smaller than, than another one that we had here. So it puts us on track to want to give something that is kind of usual in geometry. So when I say geometry here, it's more close to algebraic geometry than. But okay, so it suggests that we want to define a notion of dimension or a notion of rank. Okay, somehow we would like to say that the dimension of this set is smaller than the dimension of this one. Okay, so this is the next notion of stability, which is stronger than just stability. So it's called superstability. Okay, and so what will we say? So if you have two formulas, okay, which define non-empty sets, otherwise it's not defining non-empty sets, you will want to say that phi is greater than psi. So first of all, if you think in terms of definable set, you have phi of g and psi of g. Okay, so you want that psi implies phi. Okay, so it means that this set is contained in this set, and that phi is definable, say, over some set of parameters A, and psi forks over A. Okay, so it's exactly if we have the picture that is drawn here. Okay, so you want to define that the formula is strictly greater than another if this happens. And so then we want to use this relation to define a rank. But the problem is that, if you have an infinite descending chain of formulas like this, then it will not work. You cannot define a rank. So you said that the formula is superstable. If there is no such infinite descending chain.
Question?
Yeah.
What does it mean for phi to be definable over A?
So it means that you can that it only uses parameters in A. So like in our equation, sometimes we put parameters and that's.
A is set of parameters defining phi or any extension of it?
Yeah, any.
Quantify over A.
Sorry.
In this definition, what?
There exists A such that phi is definable over A and psi forks over A. It doesn't really matter anyway, but yeah. Okay, so right.
Sorry, I'm still a little confused because, phi is a formula to begin with, right?
Yeah.
But it comes with some parameters.
It comes with right. So it comes with some right, but maybe you can define it using less parameters. Okay, maybe you put too many.
Define the same set.
Yeah, they define the same set. Yeah, I'm talking about formulas up to equivalence in the theory. So it means think about the sets. They define the same set. The set is definable, and there is a formula defining it with parameters in A. Okay, so if phi is superstable, then we have a chance to give it a rank, which might be an ordinal. It will not in general be finite, but okay, if there is an infinite descending chain like this, then there is no hope. And we will define a group to be superstable. If any formula over G is superstable. Okay, so yeah, and then you can define the Scheller rank by induction. So you define by induction, you say so SR phi, okay. So SR of phi is at least 0 if phi of G is non-empty. Okay, and you say that SR of phi is greater than or equal alpha plus 1 if there exists a psi with whose rank is at least alpha and such that phi is strictly greater than psi. Okay, and if alpha is a limit ordinal, so think, for example, about omega, which is thought of as the limit of all the finite numbers. Say that the Scherer rank of phi is greater than or equal alpha if it's greater than or equal beta for all. Yeah. For beta strictness than alpha. Okay, and so then if your group is superstable, then you can associate the rank with every formula. So in the case that interests us, the case of the free group, this was known already. Well, this was known by an argument of Poisson, and that the free group is not superstable. So he proved it for f omega, and because of Thiel's result, then it's true also for finitely generated free groups. Okay, and in fact, I will give a proof of what it is, which is not Poisson's proof. It's really an example of a descending of a formula which has of an infinite descending chain of formulas like this. Okay, but still, it's interesting to ask. Maybe some formulas are superstable, and in that case, can we compute their rank and everything? So that's what is meant by the superstable part of the free group. Okay, so now we finished the introduction, and we can go on to proving things. Okay, so the first thing I want to talk about, and maybe it will be the only one, so is a result that is joint with the Rizos-Klinos, and which give example of non-superstable sets, or a class of non-superstable sets, or formulas. Okay, and the result is as follows. It says that if you take a formula which is defined over, say, the free group of rank n, okay, and you look at the definable set on Fn, and then you look at the set defined by the same formula on Fn plus 1, you add a generator, and you wonder whether you've gained any new elements by doing this. Okay, and the result says that if you do gain some elements, then the formula is not superstable. So Fn plus 1, then phi is not superstable. Sorry? With the natural embedding, yeah. So in fact, what this means is that, so because the embedding is elementary, then you have an embedding like this, but you want it to be strict. Okay, so I won't talk about the proof of this. I will talk about, well, I will give something a simpler example. So here what it means is that we have to find an infinite descending chain of formulas starting for phi. Okay, so I will just give an infinite descending chain of formula which is not related to phi, and then I will explain how the proof uses this. But so this is based on something that Sklinos did in his PhD. So here's the idea. Yeah, for example, yeah. So it says that there are very many sets which are. So think about f omega. So it's just a countable rank free group, infinite E1 generated by E1, E2, and so on. So let me define some sequence of elements. Okay, so it's a very hands-on proof, and I would like to understand better what's going on geometrically, but okay, it works. So the first element is E1, E2 squared, and then you take E1, E2 cubed, E3 squared, and in general the idea is that you start with E1, then you take cubes of all the generators up to I, so E2 cubed up to EI cubed, and then you take EI plus 1 squared. Okay, so you define these elements. And so you can note that BI is just BI minus 1, and you've added 1 power of EI and a square of EI plus 1. Okay, so the relation that will be important for us is that you have that if you take BI minus 1 BI and EI plus 1 minus 2, then this is equal to EI. Okay, so in particular what this gives this gives us that if I give you the elements B1 up to BI, and then I also give you EI plus 1. Okay, then so you have EI plus 1, but you can also recover EI. And then you can see by induction that you can recover all the generators before. So it means that these I plus 1 elements generate the same group as E1 up to EI plus 1, and so that this is the basis of the I plus 1 factor of f omega. Okay, let me give a name to this relation because we will be using it. And so now let me define my infinite chain of formulas. So it goes like this. Psi 1 is defined by saying that there exists, so it's psi 1 of x. Okay. There exists a y such that x equals b1 y minus 2. Okay, so where does this come from? I just look at this formula and I see that E1 is equal to b1 E2 minus 2. So see that satisfy by E1 for y equals E2. Okay? But now if I use this formula, I notice that I can write E2 as B1 minus 1 B2 E3 minus 2. Okay, and that's the idea for the next formula. I will just say that there exists a y such that x equals b1, and then I replace my y by this b1 minus 1 b2 y minus 2. Okay, so it's still satisfied by E1 because the E2 that I put here has exactly this form. So okay, for y equals E3 minus 2, E3, sorry. Okay, and then I can keep going using this formula star at every step, and in general, psi I of x, psi I of x is the resist to y, so it just says that my word is of a certain form. Okay, and this will be bi minus 1. No. bi 1 minus 2 minus 2 minus 2. Okay? So because E1 satisfies all this formula, then the psi I define non-empty sets. Okay, then also it's easy to see that, this formula implies this formula. You ask more conditions on this element y, and so in general, psi I plus 1 of x implies psi I of x. Okay, and so the last thing that we need to show to prove that this is really a descending chain is that we want to show that so that we can find a set of parameters on which psi I is defined, and such that psi I plus 1 forks over this set of parameters. So what are the parameters in psi I? Okay, maybe I should have written them here. So really psi I is psi I of x, and I use all the bi's. Okay, all the bj's up to I of b1. So what we will show is that psi I plus 1 forks over b1 bi. Okay, so how do we do this? So we need to find automorphisms that fix this b1 up to bi, and so that the translates of the set defined by this are disjoint. So the automorphism we will take are sigma n from f omega to f omega. And the idea is this: I will fix b1 up to bi, okay? And bi plus 1, I will send to bi plus n. Okay, but now we know that this can really be extended to an automorphism.
Sorry, question.
Yeah.
So the embedding of f and f omega is also elementary?
Yeah. Yeah, that's because you have an elementary chain. So if you take the union, then extend to an automorphism of f omega, which fixes, of course, b1 up to bi. And the reason you can do this is because we said that if you take, say, b1 up to bi plus n, and you add ei plus n plus 1, then you have a basis of, the first factor of f omega, and so then, okay, they're part of a basis, so you can extend. Okay, so now suppose, so what is sigma n of, let's say, psi I plus 1? I want to look at the translates of this set. Okay, so this is defined by these parameters. Okay, and so it's just the same set. Okay, here I'm just doing a manipulation of symbols. So okay, b1, bi, and here I just replace bi plus 1 by bi plus n. Yeah. Sorry? Yeah, I claim that you can extend it. So I only defined it on the first I and on I plus 1. Okay, and I claim that you can extend it to the whole of f omega. Oh. Yeah. Okay, just whichever way you like. Okay, so suppose now that two sets like this for different values of n intersect in a non-trivial way. So suppose that there exists, let me say psi I plus 1 of f omega, I'll ignore the bi's, okay, bi plus n intersect psi I plus 1 of f omega bi plus m, or let's say L, looks more different, that this is non-empty. Okay, so it means, so what is this set? This set just tells us, you know, your element, it's a word that looks like this. Okay, so then it means that there exists. So, of course, it will be for two different values of y. So let's say y and z, such that you have a word like this. So b1 up to bi minus 1, bi plus. So here I replaced the bi plus 1 by bi plus n. Okay, is equal to b1 bi minus 1 bi plus L z minus 2 minus 2. Okay, but now because we're in the free group, so first of all we can just cancel out this b1. Okay, and here there's something which says that the square of something is equal to the square of something. But in the free group it means that the two things are equal. There's uniqueness of roots. And then we can continue with this, because every time we have a square of something equals to a square of something. So in the end, we get that, okay, we get that this thing should be equal to this. We get bi plus n. I cancel out the bi plus 1. Bi plus L z minus 2. Okay, I will leave the bi's here. Okay, so now let me take bi plus L here. So okay, if you look at it, if you think about it a little bit, then you will see that this is equal to ei plus L the 1, ei. Okay, I'm assuming here, I think that L is less than or equal to n, but okay, and then cubes. Yeah. Plus 2. Okay, it doesn't matter. I plus m cubed di plus m plus n, sorry, squared. Okay, it doesn't really matter what's here, but what we see here is in particular that this element is primitive. Okay, this is primitive. But our equation here, if I put, so I put BIL here, I'll just write it down. Okay, is equal to z minus 2 y squared. And in the free group, it's not possible that a primitive element is equal to the product of two squares. Okay, so we get a contradiction. Or, maybe n equals L.
How do you say it's primitive?
Because it's just a primitive element, and then I multiply by a word which is in other generators of the basis. Okay, yeah. Okay, so in the few minutes that remain, I will just give an idea of how you prove the general theorem from this infinite descending chain of formulas. So just know that I have produced an infinite descending chain of formulas. So this is a proof that the free group is not super stable, and you actually see it in the free group and not in an elementary extension. Okay, so what we wanted to prove. Okay, just I will give you the formulas that we use. Implies phi not super stable. so what do you do? Okay, so you know that, so suppose phi is defined, so the assumption is that phi is defined over Fn, okay, with parameters in Fn. So, okay. Okay, so, and this time let me generate Fn with A1 up to An. Okay, and now I'm going to look at this free group Fn, and I'm going to take free product with my F omega, which was generated by E1 here. Okay, so it's just to make the proof more convenient. I give different names to the first n generators of this copy of F omega. Okay, so what does it mean that phi of Fn plus 1 is not equal to phi of Fn? So it means that there exists an element W in phi of, okay, even in this big thing, and which is not in phi of, okay, oh no, yeah, just phi of f of n plus 1, I will just think of it as Fn free product with I just add the first generator. Okay, and so this element I can write it as a word, okay, in E1 and then in the A's, A1 up to An. But the point is that the E1 will really appear here. Okay, and then so you can write the following formula. Okay, so when is an element in phi of x. So if, first of all, it satisfies phi, okay, remember that we want to find a descending chain of sequences which are all in phi. And then the second thing you will say is that, well, you can find a y, which allows you to write the x as w of y a1 an. And you will ask of this y that it satisfy the formula psi I that we defined here. Okay, because remember that we showed that E1 satisfies all these formulas. So this will be true here. Okay, so these are the formulas that we use. So we really use in a strong sense these formulas. But here you need to work a bit more to show that that this is actually an infinite descending chain of sequences. So, but you can do it. So you can show that.
Doesn't psi I parameter in a bigger group?
Yeah, sure. So this formula will have parameters in the bigger group. Yeah. So the chain has more and more parameters. Like the formulas have more and more parameters as you go down the chain. So yeah. Okay. So this shows that that the formula is not superstable. Okay. So I should stop here. Thanks.